A big hello to the Polygence team, judges, and my fellow Symposium scholars. I am Nathan, and I'll be sharing my project today, AI in the Sky, examining machine learning-based keystroke recognition from passive video capture. But first, a little about myself. I'm Nathan, a 19-year-old prospective computer science undergrad based in my home of Singapore. I've been working on this project the past couple of months, and I can't wait to share it with everyone. Here's an overview of what I'll be talking about today. Starting with a brief introduction, I'll bring you through some of the background about cybersecurity and AI, and also touch on what exactly my project is about. Next, in the literature review, I'll cover helpful studies that helped shape my project. Moving on to data preparation, I'll explain how I chose and pre-processed my data. Then, an overview of the actual experiments I ran before I share the results and my analysis of them. Lastly, I'll give a quick conclusion to sum everything up. Alright, so let's start with my introduction. The field of cybersecurity has rapidly evolved in importance since the internet's inception. Its importance has been highlighted on many occasions, from the far-reaching WannaCry ransomware attacks in 2017 to the politically charged attack by Russian hackers on the Ukrainian power grid in 2015. Even worse, a new tool has ended in the hands of malicious actors, artificial intelligence, or AI. Research has shown that AI systems are more than able to conduct cyber attacks and are only expected to continue to grow in competency. Here, I've outlined three research-backed dangers that AI poses. First, AI growth is very difficult to model. Currently, we have no idea whether AI will continue to grow exponentially or taper off. We must thus prepare for the worst-case scenario, where AI grows at a pace that regulation and defense cannot keep up with. Second, the issue of AI alignment. Alignment is a technical problem of imbuing AI systems with ideals and ethical principles. If AI research does not progress at the same speed as alignment research, we could have AI research that far outstrips alignment research, leading to misaligned AI that could be easily misappropriated for cybercrime. Lastly, AI possesses the first mover advantage. Because we don't know how AI will continue to develop in cyber attacks, we will always be reactive in our defenses. If we are unable to react sufficiently fast to new attacks, cybercrime will rise in prevalence. So far, we've talked about cybersecurity in terms of viruses and system penetration. However, what if a bad actor were able to steal your private data without penetrating your system? Enter side channel attacks. These are attacks that exploit information leakage indirectly by the system during its operation, rather than breaking the system's intended security mechanisms directly. This means that even if you're diligent, never clicking on phishing links, never opening random emails, and always being careful about the sites you visit, your information could still be leaked. How? Well, let's look at some examples. Here are three examples of side channel attacks. To elaborate on just one, acoustic emanations of a physical keyboard can be used to pinpoint keystrokes and deduce sensitive information such as passwords. This information can be extracted from something as simple as a handphone microphone, not requiring bad actors to hack your device at all. Today, we're focusing on one particular side channel attack, visual hacking, also known as shoulder surfing or visual eavesdropping. This involves inferring keystrokes via passive video of the person typing. This is a very real-world problem. For example, people conducting banking operations on their computers in public areas like cafes or libraries could easily be victims of visual hacking. In this paper, I shall explore the use of AI, more specifically vision-based machine learning, in optical side channel attacks involving keystroke inference from passive video capture. I hope this introduction has caught you up to speed. Now, let's talk about the helpful literature I found. I chose to showcase the top three papers that explored the most similar threat spaces to ours. These papers were chosen to provide a range of different methodologies, conclusions, and focuses. These are the three studies. I will go over the major takeaways from each paper without delving too much into the details. Interested parties can find the links to the papers in my references section. Here's a quick summary of our key takeaways. First, frame-by-frame analysis is the norm for these projects. This means that each frame of a video is the input for the neural network, with the output being a labeled keystroke. As such, this problem becomes a classic AI classification problem. Next, I want to attempt optical flow analysis, also known as introducing temporal context. This means for every frame depicting a keystroke, the network is also fed the frame before and the frame after. It's been found that in some studies, this is unable to boost performance, but I felt that this approach still had much potential and I wanted to give it a shot. Last, the studies limited the keystrokes recognized to just the alphabet and a few additional tokens, such as the space character. This is because too many labels, such as introducing capital letters and punctuation, could confuse the algorithm. As such, I chose to adopt this as well. With the literature review completed, I was ready to start data preparation. This is a critical step. One study suggests that such preparation work comprises 80 to 90% of the project itself. The common axiom of garbage in, garbage out holds true, whereby the quality of the output from a neural network is only as valid as the data that is fed in. I used the publicly available keystroke typing videos dataset. This is hosted on Hugging Face and posted by user Andrew Tran in 2025. This dataset comprises 800 videos with a mean video length of about 6.73 seconds. This gave me a database of 160,000 frames and 40,000 keystrokes, totaling about 90 minutes of footage. This dataset was chosen as it is the most appropriate dataset publicly available. The video data had consistent user typing, a consistent keyboard, a consistent camera angle, and lighting was also largely consistent. Keeping these factors controlled was imperative to ensure that prospective AI trained on such a dataset would only generalize based on hand placement and key presses, not on other features. There was also meticulous labeling of the timestamp information of key presses, thus ensuring that frame-by-frame analysis was possible. However, this dataset was not without its problems. Chiefly, it was unevenly distributed, as seen on the screen above. Majority of the frames were nothing frames where the hand was moving between keystrokes and did not actually type anything. Furthermore, while some keys were pressed thousands of times, others were only pressed a handful, with 2 keys being pressed once total. I needed to clean up the data. Thus, I decided to merge classes, such as upper and lower case key presses, and also removed rarer classes such as punctuation. I also randomly removed 95% of nothing frames. This helped even out the distribution seen on screen. Another big issue was the dataset file size. Each image was in high resolution, leading to a large total database size of 58 gigabytes, with it taking 8.7 minutes per epoch to train. The image also included redundant pixel data, such as the area outside the keyboard, as well as color information, which I worried would confuse a neural network. The solution was to transform the data. I chose a 4-step transformation. First, I grayscaled the image, then contrast boosted it before applying a crop. This worked, reducing the dataset size to just 6 gigabytes and training time to 1.4 minutes per epoch, a significant increase for efficiency reasons. This was also hypothesized to aid with training accuracy due to the smaller size that included only the most important features. Now that the data is sufficiently prepared, we can finally move on to the actual experiments. The aim of our experiments was to create a model that would take in a prompt, that being a frame, and an output label guess, whether this be a letter, and output a label guess, whether this be a letter, a symbol, or a nothing token. To achieve this, I had to train a model. I inputted 40,000 pairs of frame and labels into the neural network, which then blindly guessed labels. Loss, which is the difference between the actual label and the guess, was then calculated before being fed into the complex backpropagation algorithm. This would then tweak the weights of the neural network so as to achieve a better outcome. Each cycle is called an epoch, with training runs consisting of multiple epochs. In total, I conducted 26 successful training runs, which each run consisting about 60 to 100 epochs, and took between 2 to 13 hours between each training run. The total time spent training was 75 hours. Our contribution to this field was to synthesize the fundamentals of keystroke inference models and construct a baseline model with a reduction in complexity. I conducted a total of 9 experiments in order to test different hyperparameters and their importance. This can be seen on the screen above. These are the experiments that yielded interesting results, and thus will be the ones that we'll go through today due to the lack of time. Interested parties can check out my paper where I go over all 9 experiments. Here's a bit more detail about these 3 experiments that we will be discussing. First, evaluating data transformation. As mentioned in the previous section, I did a lot of data preparation work, and thus I would like to verify that this kind of work was useful for the actual model training. As such, I will be comparing models trained on unprocessed data versus processed data. Second, evaluating different models. I compare models built on different architectures, including convolutional neural networks called CNNs and a feed-forward architecture. To give a quick rundown, CNNs are more modern, and we're looking at EfficientNet, ResNet, and MobileNet today. Feed-forward models are older and poorer at spatial feature extraction. They are expected to perform worse and are here for baseline comparisons. The last experiment will be to evaluate time context. As mentioned in the literature review, I was interested to attempt optical flow analysis to come to my own conclusions. As such, I compare models trained on 1 frame to 1 label data versus 3 frames to 1 label data. 3 frames to 1 label refers to data where, for any keystroke that occurs, I included the frame before and after. This aims, of course, to introduce temporal context to the AI model. Now, moving on to our results and discussion section, where I will discuss the outcomes of these 3 experiments. Before we go over the actual data, let's talk about evaluation metric. This is a standard metric in machine learning studies, and it combines both the precision and recall into a single score, the F1 score. It is especially appropriate when dealing with imbalanced datasets, and if you remember, our dataset was rather imbalanced even after pre-processing. Accuracy alone would have been misleading. The F1 score formula, shown on the slide, is well-documented in literature as a robust metric. We will discuss other data points as well. Training loss quantifies the error between our model's predictions and actual labels while training. Decreasing loss shows the model is learning. Validation loss quantifies how the model performs on data it was not trained on, and high loss indicates overfitting, the phenomenon where the model memorizes the labels for training data. This is bad since it means that the model is not generalizing patterns. Lastly, validation accuracy just refers to the proportion of character guesses the model got correct in the validation dataset. A higher score is better, as it means the model is better at predicting. However, we will still use the F1 score for final judgments due to the weight bias nature of validation accuracy. Okay, let's start with our first experiment, evaluating data transformation. When we look at the training loss, we see a clear difference. The models trained on transformed data decrease much faster when it reaches a lower loss value. This indicates data transformation allows for training that is able to converge faster and up to a more accurate answer. Looking at validation loss, we see that irrespective of data transformation, overfitting occurs around epoch 13. Finally, the F1 score confirms the original trend seen in the training loss. With data transformations, our model reached an F1 score of 0.499. Without them, it barely reached 0.127. That's a huge difference, more than triple the performance. We can thus conclude that data transformation allows for superior model training and performance. Simple pre-processing of data matters a lot when it comes to model outcomes. In terms of training speed, now we'll move on to evaluating different models. In terms of training speed, EfficientNet was the fastest, seen by how its training loss curve converged the fastest. On the other hand, the feed-forward model was the slowest, with a curve that began plateauing above all the others. EfficientNet also plateaued at the lowest epochs, indicating best training accuracy. For validation loss, we see an interesting trend. In all 3 convolutional models, the validation loss decreased initially but began rising again after about 10 epochs. This is a clear sign of overfitting. The feed-forward network, in contrast, does not show the same overfitting pattern. Its validation loss remains low and unstable throughout training. I, however, suspect that this displays underfitting, considering that training loss was so high in the previous graph. The model is likely struggling to extract patterns. The F1 score gives us another angle. Here, MobileNet V2 comes out on top, reaching an impressive peak of 0.510. The feed-forward model, as expected, performs poorly. The CNNs that overfit early on taper off in the F1 scores after initial improvement. When we turn to validation accuracy, an even more interesting pattern emerges. Early on, MobileNet V2 appears to be the clear winner, peaking around epoch 18. However, after epoch 40, the feed-forward model continues to improve its validation accuracy even when the others decline. This may make it seem as though the feed-forward model is superior. However, to analyze, I see that the low F1 score suggests otherwise. I suspect what was actually happening was that the feed-forward model had likely learned to cheat by guessing the majority classes that dominated the dataset, things like nothing or space. Its F1 score indicates it was not generalizing well to less frequent classes. So the conclusion from this experiment is that MobileNet V2 is the best architecture overall by a slim margin. The feed-forward model's poor performance indicates that spatial feature extraction is needed for this problem. Convolutional architectures, chief among them being MobileNet, remain essential for this kind of vision-based classification. Lastly, let's evaluate time context. Time context can improve the rate of learning provided in use with convolutional neural networks, as seen from this training loss graph, where time context-informed CNNs are converging faster and at lower loss. Time context with a feed-forward architecture appears to perform poorly. Looking at validation loss, we can see that irregardless of time context, there are signs of overfitting. However, interestingly, time context seems to worsen overfitting, seen by how the CNNs with time context start overfitting at epoch 10 versus epoch 13 for the model without time context. Looking at F1 score, we can see that the time context with pre-trained ResNet had the highest F1 score of 0.518, outperforming F1 scores without time context. Time context with feed-forward model scored the worst, with highest F1 score of only 0.49. Looking at validation accuracy, we see similar results with time context trained CNNs performing better than without time context, and the feed-forward model performing the worst. In conclusion, time context does allow for improved training and performance. However, the model used is very important, with CNNs and particularly pre-trained CNNs performing the best. Finally, our conclusion. In summary, data preparation provides a large improvement in performance and training. MobileNet v2 is the leading architecture for this problem, and temporal context is effective at improving results. In this study, I was able to create a suitably generalized model that was trained on a limited and flawed dataset using an unsophisticated model. I managed to achieve a peak F1 score of 0.521 and a best character accuracy score of 48.3%. For future research, I want to look at the blind recognition of keystrokes, which is where keystrokes can be recognized from just hand placement and movement without an image of the keyboard. This is to improve the model for a realistic attack scenario, where capturing a clean overhead shot of the keyboard with keycap labels is unlikely. Next, I want to research methods to counter visual keystroke inference, as it is important to defend against such malicious attack vectors. Lastly, keystroke inference on mobile phone keyboards is another area that I want to explore. It would be a similar project with passive video collection of mobile phone keyboards instead of laptop keyboards. This was chosen since in modern times people conduct sensitive operations on their phones as well, such as mobile banking. This could thus place phone keyboards as targets for attacks. Here are the references I have used. I have bolded the 3 sources outlined in the literature review for your ease of referral. I've come to the end of my presentation. Thank you so much for your kind attention.